Welcome back to the Deep Dive. Today we're looking at some really revolutionary research that seems to rethink the core architecture of large language models.
Yeah, this comes from a team at NVIDIA and the University of Chicago. It's a new hybrid model they're calling TiDAR.
TiDAR, which stands for Think in Diffusion, Talk in Autoregression.
That's the one.
So for you listening, our mission today is pretty straightforward. We want to understand how TiDAR is claiming to solve what is, probably the single biggest trade-off in LLM performance.
Right, the balance between speed and quality.
How do you get that lightning-fast parallel generation, but also keep the perfect sentence-level coherence you need for high-quality output?
And that trade-off really defines the whole field right now. On one side, you have your standard autoregressive models, or AR models. Think your GPTs, your llamas.
The big names.
The big names. They get incredible quality because they generate one token at a time based on everything that came before. Very coherent.
But the downside is they are just so slow, one token per step, and they're totally memory-bound.
And then on the other side, you have diffusion language models, DLMs. They promise this huge speed up because they can decode a bunch of tokens all at once, in parallel.
But that's where the quality hit comes in, right?
It is. That parallel generation kind of assumes the tokens in that step are independent of each other. It's like writing through words at once without checking if they flow. So the quality usually suffers compared to the AR models.
So the goal here, the big ambition with TiDAR, is to get the best of both. To take the throughput and the GPU power of diffusion, the thinking, and fuse it with that clean AR-level quality, the talking, and do it all in one model.
And to really get how they did it, you first have to understand the real bottleneck when you're running these AR models, especially for, say, a single user query where the batch size is small.
Yeah, let's unpack that. I think most people assume model speed is just about how fast the GPU can do the math.
That's the common intuition, but the reality at small batch sizes is quite different. The latency isn't from the computation. It's almost entirely dominated by memory operations.
So, loading the model weights from memory.
Loading the weights and also handling the key value cache, the KV cache, for all the tokens you've already generated. That's the choke point. Memory bandwidth is saturated.
So the computer isn't spending time thinking. It's spending its time rummaging through a giant filing cabinet to find the right files before it can write the next word.
That's a great analogy. And this is where TiDAR's core insight comes from, something the researchers found by profiling these systems. They realized you can leverage something they call free token slots.
Free token slots. That sounds almost too good to be true. What does that mean in practice?
It means that since you're already paying that heavy cost to load the weights and KV cache for one token, the extra cost to generate a second or a third or maybe even an eighth token in that same forward pass is tiny.
Because they share that initial memory loading cost.
They're essentially free from a latency perspective up to a certain point. TiDAR is built from the ground up to just jam as much parallel work as possible into those free slots.
Okay, but then we're back to the quality problem. If you're just generating tokens in parallel, how does TiDAR avoid that coherence breakdown that other diffusion models have?
Well, see, that's the key. A standard DLM tries to predict cat, sat, and on all at once. The prediction for on can't know if the model chose sat or slept. That's the independence assumption that hurts quality. TiDAR gets around this by making the parallel work only for drafting, not for the final answer.
Ah, okay. So let's get into that dual identity. Think in diffusion, talk in autoregression. That name really says it all.
It's the absolute heart of it. TiDAR does its parallel work, the thinking using diffusion, which is fast, but the final high-quality sampling, the talking, is still done with the high-fidelity autoregressive method. And the magic is it does both in a single, simultaneous computation.
So walk me through that. What's happening in one forward pass? You said the input is partitioned somehow.
It is. So instead of one long sequence, the input tokens are broken into 3 sections. First, you have your history, the prefix tokens. The model just reuses their KV cache.
Standard stuff.
Then the second part. This is a small number of tokens that were proposed in the last step, and now they're being verified and sampled the AR way, the high-quality part.
And the third section must be the diffusion part.
Right. A much larger block of tokens that are being pre-drafted for the next step. That's the parallel diffusion-based thinking.
So it's looking back, looking at the present, and guessing about the future all at once, but treating each part differently.
Precisely. And to make that 3-way process work, they had to invent a new kind of attention mechanism. They call it the structured causal bidirectional hybrid attention mask.
Okay, that is a mouthful. What does that do in simple terms?
The attention mask just tells a token which other tokens it's allowed to look at. A normal AR model uses a causal mask. A token can only see the past. Diffusion uses a bidirectional one. It sees everything.
And this one is a hybrid of the two.
It selectively applies both. It lets the diffusion part see everything bidirectionally, which is great for fast drafting, but it forces the autoregressive part to stick to strict causality, which is what preserves the quality. It's the plumbing that makes the whole thing work.
And what's interesting is that this complexity in the architecture actually leads to a much simpler training strategy, right? They sidestepped a lot of the usual diffusion model complications.
They really did. It's an elegant solution. Instead of complex noise schedules or random masking, they just set all the tokens in that future drafting section to be a special mask token during training.
And what does that buy them?
3 huge benefits. First, it gives the model a much clearer, denser training signal for the diffusion part. Second, it makes balancing the 2 different loss functions, the AR loss and the diffusion loss, way easier.
And the third?
And this is critical for speed. It trains the model to be really good at one-step diffusion drafting during inference. It's a smart training choice that directly helps the inference speed.
Okay, so if you zoom out, this whole structure sounds a lot like speculative decoding,
It absolutely is a speculative framework, yeah.
where you have a fast model that proposes tokens and a slower, better model that checks them. But TiDAR seems to be, I don't know, a supercharged version of that idea.
It is. The diffusion part is rapidly drafting a bunch of speculative tokens in parallel. Then the autoregressive part comes in and uses rejection sampling to check them for quality.
So what's the big advantage here over a more traditional speculative setup, where you might use a separate, much smaller model to make the drafts?
The biggest difference is that the drafting and the checking happen at the same time, in a single forward pass. Most other methods have this sequential overhead. The big model has to wait for the little draft model to finish its guess.
And TiDAR eliminates that waiting time.
Completely. It pre-drafts proposals for all possible outcomes of the current check. It's essentially guessing and checking in one single fused step.
But doesn't using the big base model for drafting add its own overhead? A small draft model is small for a reason. It's fast.
That's a great question. And the answer goes back to those free token slots. By using parallel diffusion for drafting, the latency cost of using the bigger model is basically absorbed. It ends up being superior for 3 reasons when you compare it to other frameworks.
What are they?
1, the draft model is the base model, so the drafts are super high quality. 2, the drafting is fully parallel, so it uses the whole GPU. And 3, as we said, doing it all at once kills that sequential overhead.
So they trade the simplicity of a tiny draft model for the pure, latency-free parallelism you get with diffusion.
They do. And they also solved a key engineering piece. TiDAR supports what's called exact KV cache.
What does that mean for performance?
It means the model never has to recompute the cache for any token, even for the ones that get rejected. It keeps the whole process incredibly efficient.
Which brings us to the results. After all this clever architecture and training, what's the actual payoff? The numbers have to be good.
They are more than good. They're pretty stunning. The TiDAR 1.5 billion parameter model got an average speedup of 4.71 times in throughput over its AR equivalent.
Nearly 5 times faster.
5 times faster. And they report this was with lossless quality.
Wow. I mean, a nearly 5x speedup is a game changer. That could slash serving costs or enable new real-time applications that were just too slow before.
And it scales up. The bigger 8 billion parameter TiDAR model hit a 5.91 times speed up over its counterpart with what they call minimal loss in quality.
You can see that efficiency in the tokens per NFE metric, right?
Yeah.
The network function evaluation. It shows how much work they get done in one pass.
That metric really tells the story. The 1.5B model spits out 7.45 tokens per pass on average. The 8B model gets 8.25. It just confirms they are maxing out those free token slots.
And how does it compare to other parallel models, both diffusion and speculative?
It pretty consistently beats other open source diffusion models like Dream or Llada on both quality and speed.
So the hybrid design is just better.
And what's more, they showed it surpasses the gains from even state-of-the-art speculative decoding methods like eJolie-3. The paper says this is the first time a diffusion-based model has shown this kind of speed-up in latency-critical use cases.
And one last thing on quality AR models are great for things like evaluating multiple choice questions because of their causal structure. Does TiDAR lose that?
Nope, that's another strength. Because it has that native AR mode built right in, it can do those likelihood tasks just as well as a traditional AR model. You're not giving anything up.
So to synthesize this, TiDAR really operationalizes that free token slots idea.
Yeah.
It uses one model to draft fast with diffusion and sample carefully with autoregression all at once.
That's the takeaway. It's the first architecture that's really been shown to close that quality gap with AR models while delivering just a massive throughput improvement. You get the parallel thinking and the sequential talking in one efficient step.
This has huge implications for deployment right now. But as always, there's a next challenge. The paper mentions a limitation with their current training setup,
That's right. To make it work, they essentially have to double the sequence length during training to add all those masked tokens for the diffusion part.
which means double the training cost, more or less.
And that's the key challenge ahead. The model itself isn't limited in long context, but the training method is expensive. So the final thought for you to consider is this. How can we keep this incredible 5x inference speedup, but without bloating the training costs for the truly massive models of the future? Finding an efficient way to extend this to long context is where the next breakthrough will be.